Hello everyone, welcome back to this lecture series on vector calculus. Today we are going to talk about vectors, the scalar product and cross product, derivative of a vector, gradient and directional derivatives. Okay. So first we take the definition of a vector. So the quantity represented by the directed line segment AB with the initial point A and terminal point B is a vector, and its length is denoted by the magnitude of the line segment. The quantity here can be like the force or displacement or velocity, the arrow points uh, in the direction of the action, and its length gives the magnitude of the action in terms of the suitably chosen units. Okay. We can have vectors in two dimension, which can be an ordered pair, or we can have a three-dimensional vector of ordered triplet of real numbers. Uh, uh, Two vectors will be said to be equal, okay, if they have the same length and direction. Okay. Uh, if we have a vector v, which is two-dimensional vector in the plane equal to the vector with initial point at origin, okay, that means with respect to its standard position, and terminal point as a ordered pair v1 v2, then the components of vector v can be written as v1 comma v2. Okay, so where v1 v2 are components of vector v uh, with the initial point origin and the terminal point as v1 v2. Okay. Similarly, we can have a vector in three dimension or even in higher dimensions uh, with the standard position as origin and terminal point at v1 v2 v3. So v1 v2 v3 are actually the components of the vector, and we can write that vector v in this form also. Okay. uh, the magnitude or length of the vector uh, v, uh, which is uh, the magnitude of AB, okay, is the non-negative number. Magnitude of V or length of V is square root of V1 square plus V2 square plus V3 square. Okay, or equivalently it can be written as square root of x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 squared. Okay, where x1 y1 z1 uh, is the point or position vector of A, and x2 y2 z2 is the position vector of B. Okay, and clearly V vector is like the standard position vector parallel to the AB vector. Okay. uh, the vector addition and the scalar multiplication is defined on vectors. That means we can add vectors by adding the corresponding components, and we can multiply any vector by a scalar by multiplying each component by the scalar. Okay. Um, some of the properties of vector operation. So let if u, v, w be vectors and a and b be scalars, then uh, we can add two vectors in any order. That means addition is commutative. So if we can add u plus v or v plus u, they gives the same result. Okay. The second property is the associativity. That means if we add two vectors u plus u and v and then add a third vector w, or we add the two vectors v plus w and then add u to it, okay, it gives the same result. Okay. U plus 0 vector is u vector. Okay, so if we add 0 vector to any vector, it gives the uh, same result. Okay. uh, the fourth is u vector plus minus of u vector is 0 vector. Okay. Fifth, the scalar multiple of a vector where scalar is taken as 0, okay, is a 0 vector. Okay, so any vector can be when multiplied with a 0 scalar will become a 0 vector. Okay, u vector times 1 is u vector itself. Okay, so the scalar 1 is multiplied to any vector, it gives the same vector. A times b times u vector is same as ab times u vector. Okay, so that means if I scale the vector u with b and then the new vector, if it is scaled by another scalar a, it is same as the u vector is scaled by a product of ab. Okay, uh, a times u plus v is a times u vector plus a times v vector. Okay, so that means if we add two vectors and scale it, or if you scale the vectors first with the same constant and then add the vectors, it gives the same result. Okay, and say a plus b times u vector is au vector plus bu vectors. Okay, so if you add two scalars and then scale any vector u with the sum, is same as that you scale the u vectors with one scalar and with other scalar and then add these two vectors, and it gives the same result. So these are some of the properties of vectors. Now the unit vector. Okay, so any vector is uh, set to be unit vector if it is of length 1. Okay, so a vector v of length 1 is called a unit vector. The standard unit vectors are denoted by I cap, which is 1 0 0. Okay, j cap as 0 1 0 and k cap as 0 0 1. Okay, if we are working in three-dimensional space, and if you have x-axis, y-axis and z-axis, so I cap 1 0 0 is the unit vector in the direction of x-axis. J cap 0 1 0 will be the unit vector in the direction of y-axis, and k cap 0 0 1 is the unit vector in the direction of z-axis. Uh, any vector v in having in three-dimensional space with ordered triplet as v1 v2 v3 can be written as a linear combination of these standard unit vectors, as v vector, which is a triplet, can be written as v1i plus v2j plus v3k. Okay, so I, j, k are the unit vectors in the direction of x, y and z respectively. Okay, and whenever v is a non-zero vector, so the length of the vector which is denoted by magnitude of v is also non-zero, and uh, this will hold that if we divide the vector with its magnitude, then the magnitude of the whole thing will be 1. Okay, so that means if I divide any vector with its length, then that vector satisfies the property that the new vector has a length of 1. Okay, so that means we can generate a vector of length 1, or means we can generate a unit vector from any vector any non-zero vector by dividing with its magnitude. Okay, so this means that if I divide any non-zero vector with its magnitude, then this new vector is a unit vector in the direction of v itself. Okay, in the same direction. Okay, so if you are given any non-zero vector and we want to find a unit vector in the direction of that vector, then we just need to divide the vector by its length to generate that unit vector. Okay, then second definition is the scalar product, or we also call it as the dot product, or we also call it inner product of vectors. See, the dot product or scalar product is denoted by u vector dot v vector, or we call it u dot v. It is a dot product of two vectors u and v, where u vector, say in three-dimensional space, u vector is u1, u2, u3 components, and v vector is having components v1, v2, v3, and this dot product is the scalar defined to be the sum of the product of corresponding components. Okay, so u1 v1 plus u2 v2 plus u3 v3. Okay, and this can be written as same as the length of u times length of v times cosine of theta, where theta is the angle between the vectors u and v if we consider that they have the uh, same initial value. Okay, say taken to be origin. Okay, so from origin, if you have a vector u and a vector v, and the angle between two is theta, where theta lies between 0 and pi, then the scalar product can be calculated using the components, or can be calculated using the magnitude with the angle. Okay, uh, so clearly this dot product of vectors will be a scalar quantity. Okay, and that's why we are also saying it as a scalar product. The geometric significance of or interpretation of the scalar product goes like this: that if you consider two vectors, say u vector is pq vector and v vector is ps vector. Okay, so if you are given a vector u which is in the direction of p to q, and there is a vector v which is p to s. Okay, and let theta is the angle between the vectors u and v, so theta is the angle here. Okay, and let PR be the projection of u onto v. Okay, so let this PR is the projection of this vector u on v vector. Okay, then clearly PR vector will be the magnitude of u times cosine of theta times cosine of theta. Okay, because clearly this is uh, the base over the hypotenuse from this triangle. Okay, so I guess there needs to be magnitude here. Okay, and so the dot product u dot v, which by definition is magnitude u times magnitude v times cosine of theta, uh, since u times cosine theta is magnitude pr, so it will be magnitude of v times the pr, and so where pr we said is the projection of the vector u in the direction of or on the v vector. Okay, so the dot product or scalar dot product of u and v is the magnitude of one of the vectors times the projection of the other vector in the direction of the first vector. Okay, so the scalar product of two vectors uv is the product of length of one of the vectors, so product of length of v vector and length of the projection of u in the direction of v. Okay, so it is the length of the v vector times the length of the projection u in the direction of v, which is this PR. Okay, so that's what the scalar dot product gives us. Okay, uh, the some of the properties of scalar dot product. Okay, so if you have vectors u, v and w, and c is any scalar, then the dot product is commutative. That means u dot v is same as v dot u. uh, the dot product, when if we scale one of the vectors with a constant c and then take dot product of v, it is same as if we scale the second vector with the same scalar c and take dot product with u, or if we take the dot product first and then scale it, okay, with the same constant. It all these three gives the same scalar quantity. Okay, uh, third is that u dot v plus w is same as u dot v plus u dot w. Okay, so if we add two vectors and then take a scalar product with u, or if you take the scalar product of u with v and with w and then add the vectors, it gives the same result. Okay, the dot product of vector with itself is length squared. Okay, so u dot u is magnitude u square. Okay, and the dot product of any vector with zero vector is a zero scalar. Okay, so clearly zero is a vector, but here on the right hand side it's a scalar because dot product is a scalar quantity. Okay, so uh, say if we, that means if we have to do the dot product of the I, j and k vectors, so this fourth result immediately says that I dot I will be magnitude of I square and magnitude of unit vector is 1, so that means I dot I will be 1. Okay, similarly j dot j will be 1, and the k dot k will be 1. Okay, the I and j vectors or j and k vectors, they are orthogonal. Okay, so for orthogonality of vectors, any two vectors u and v are orthogonal or perpendicular if their dot product is exactly 0. Okay, because dot product of two vectors is magnitude of first into magnitude of second into cosine of the angle, and if they are perpendicular, so cosine of angle will be 0, cosine t will be 0, so it will give a 0 value. Okay, so that means the unit vector in the direction of x, y, z, they are orthogonal, so their dot products must be 0. So I dot j is 0, j dot k is 0, and I dot k are 0, and then we can reverse them to write j dot I is also 0 because of the first property, they are commutative. Okay, gives the same value. uh, the second definition that we are going to take is the cross product of two vectors in space. So consider two non-zero vectors u and v in space. Okay, uh, if u and v are not parallel, they will determine a plane. Okay, so if you have a vector u, you have a vector v, and they are not parallel. Okay, so making angle say theta, which is not equal to 0 or not equal to pi, then they will lie in a plane. Okay, and so if we select n cap to be the perpendicular vector to this plane by right hand rule, that means if I move from u to v with the right hand fingers curled uh, through an angle of theta from u to v, then the direction of thumb will tell us the vector or direction of this n cap unit vector. Okay, so if this n cap is perpendicular to both u and v with a right hand curl, then the cross product of u and v is denoted by u cross v, and we call it u cross v, and is given by the magnitude of u, the magnitude of v sine theta times n cap, where n cap is the this unit vector perpendicular to both u and v, and the term u magnitude, v magnitude, and sine theta is a scalar times this n cap vector. So this whole quantity is a vector quantity. Okay, and theta is any angle between 0 and pi. Okay. Uh, so the two vectors will be orthogonal. Okay, u and v. Uh, are uh, orthogonal. We said its dot product is 0, but clearly u cross v is in the direction of n cap, and n cap is perpendicular to u and v. So u cross v is perpendicular to both u and v vectors. So that means u cross v vector is orthogonal to u vector as well as v vector. Okay, the cross product will be 0 only when either sine theta is 0, that means theta is 0 or pi, or when the u vector or v vector are one of them are 0 or both are 0 vectors. Okay, in either of these cases the cross product can be 0. Okay. uh, Okay, so clearly if you have parallel vectors and if non-zero vectors u and v are parallel, okay, so the cross product has to be 0, because if they are parallel then theta will be either 0 or pi. Okay, so it will give the 0 value. Okay. uh, some properties of cross product of vectors. The if you have a u, v, and w as any vectors and r as any scalars, uh, then uh, if you scale one vector u with r and scale other vector v with s and then take cross product, it is same as taking cross product of the vectors first and then scaling it with the product rs. Okay. uh, the u cross v plus w is same as u cross v plus u cross w. Okay, so if you add two vectors v and w and then take the cross product u with this sum is same as you take the cross product first and then add those two vectors. Okay, in cross product the order has to be maintained. Okay, u cross v is not equal to v cross, so in fact it is the negative of v cross u. So that's our third property, that v cross u is negative of u cross v. Okay, so u cross v we have to use right hand such that curl is from u towards v, so its thumb will be upward. Okay, but if we are taking v cross u, so if we use the right hand to curl it, then the thumb direction will become downwards. Okay, so v cross u will be downward, u cross will be upward, so they are just the negative of each other. Okay. uh, the fourth is that the sum cross with u is v cross u plus w cross u. Okay, so it's just similar to this. Okay, the order has to be maintained. Okay, so because v cross u is minus of u cross v, so we cannot write u first. Okay, uh, zero vector cross any vector is zero vector. Okay, so that is clearly true. And the sixth property is that u cross v cross w is u dot w times v minus u dot v times w. Okay, so clearly you can see that here dot product means just a scalar quantity, here also dot is a scalar, so you have a difference of vectors, and here it is cross product of three vectors. Okay. So geometric interpretation of cross product. So if I calculate the magnitude of u cross v, okay, then it will be magnitude of uh, u cross v is magnitude u, magnitude v, sine theta and cap. So magnitude will make magnitude of this, and n cap is a unit vector, so its magnitude is 1, so we can simply write the magnitude u, magnitude v of sine theta. And if you have u vector, v vector with angle theta, so you can clearly see that the height uh, by the length of hypotenuse will be sine of theta, so height is nothing but magnitude of v times sine theta, and the length of u is base, and so base into height will be the area of this parallelogram. Okay, so clearly the cross product magnitude will determine the area of the parallelogram. Okay, where u of the parallelogram such that u and v vectors form their sides. Okay, uh, we can calculate cross product if u and v vector are given by calculating the determinant. Okay, so if u vector is a vector in space written as u1 I cap plus u2 j cap plus u3 k cap, and v vector is another vector in space, then u cross v can be calculated by the determinant where first row is written as the unit vector in the direction of x, y, z. Second row is written for the vector components of u vector, and third row as the components of v vector. Okay, so we can take the determinant or write the determinant, open this, and then that will give us the vector u cross v, which will be perpendicular to both vector u as well as vector v. Okay, uh, say for example, find a unit vector which is normal to both u and v. Okay, so we know that this cross product of vectors is normal to both vectors, and so we can calculate u cross v, that will be a vector normal to both these, and then to find the unit vector we just need to divide the u cross v vector with its magnitude. Okay, so we can calculate u cross v by writing in the first row as unit vectors, in the second row the components of u, which is 2, 1, minus 1, and in the third the components of v, 1, 1, 2. Then we can open the determinant, so I cap times 2 plus 1, so we get 3i, minus j times 4 plus 1, so minus 5j, and k times 2 minus 1, so that's 1 times k cap. And if I divide this with its magnitude, so magnitude will be this square plus this square plus this square under root. Okay, so 9 plus 25 plus 1 under root, so that will be root 35. So if I divide this by root 35, so that will be the unit vector. So unit vector in the direction of u cross v is 1 by root 35 of 3i minus 5j plus k. So next definition is the differentiation of a vector. So let there is a vector function r which is equal to f I cap plus g j cap plus h k cap, where f, g, and h are differentiable functions of t, and so the derivative of the vector function is given by r dash t or dr by dt, which is limit delta t tends to 0 r at t plus delta t minus rt over delta t. Okay, and if this limit exists, then we say that this vector function r is differentiable. So if for this definition, it is very similar to the definition that we did in differential calculus, and here you can suppose say that r is a position vector, say, of a particle moving along some curve in space, and so this numerator is the difference between the position vector at any time t and at any time t plus delta t, where delta t is a small change in time. Okay, and uh, um, this divided by the delta t, if delta t goes to 0, this, if this limit exists, then it will be the derivative of the vector function r with respect to t. And since r is ft plus gtj plus htk, so we can write rt as this, and rt plus delta t will be change in t as t plus delta t. So we can separate into ij, k, and by definition of differential calculus we can write it in this form as df by dt I cap plus dg by dt j cap plus dh by dt k cap. Okay. uh, this vector function r will be said to be differentiable if it is differentiable at every point of its domain, similar to what we did in differential calculus. The curve that will be traced out by this function will be said to be smooth if this derivative is continuous and never zero. Okay, so if it is never zero, that means the uh, these derivatives f by t, g by t, and h by t, they cannot be simultaneously zero. Okay, so if f g h has a first derivatives which are continuous but not simultaneously zero, then we say that this curve is a smooth curve. Okay. um, Geometrical significance of this derivative. Okay, so say you have a point P on the curve, okay, whose position vector is uh, r, and uh, there is a neighborhood point which is after time t plus delta t, so whose position vector is r t plus delta t, and so the vector pq uh, is represented by this r plus t delta t minus of rt, and if delta t is positive quantity, then uh, by property this vector, if it is scaled by a delta t, that means if I multiply this by 1 by delta t, that will be a vector in the same direction as of pq. So this new vector, if I multiply by delta t to this, okay, then this new vector will be in the same direction of pq. And so if delta t limit goes to 0, if we move q towards p, this vector will become tangent at p. Okay, so that's exactly what we had in differential calculus. It same extended to these vectors. So for delta t greater than 0, if we scalar multiply with 1 by delta t this quantity, then it points in the same direction as the vector of pq, and as delta t goes to 0, this vector approaches a vector that is tangent to the curve at p. Okay, and so the vector r dash t, when different from 0, is defined to be the vector tangent to the curve at p. And so that's this derivative is the tangent vector to the curve at the point p. Okay. uh, so one result that if r is a differentiable vector function of t of constant length, then the scalar product of r with its derivative is exactly 0. Okay, so we can prove this easily, that let r be a differentiable vector function of t of constant length. That means the length of the r is constant, so if we square it, we can write that the length squared is c square, and we know by property u dot u is length squared, so r length squared can be written as r dot r. Okay, and if we differentiate this with respect to t, then on left hand side we can use the derivative of product rule to write it as dr by dt dot product with r plus r times, or r dot product with dr by dt equal to 0. And since scalar product is commutative, so dr by dt dot r is same as r dot dr by dt, so they add up to 2 times. Okay, and so it immediately gives the result that r dot dr by dt is exactly 0. Okay, Uh, Another definition is the del operator or the Nabla operator. The operator written by this symbol and defined by uh, I cap times derivative with respect to x plus j cap partial derivative with y plus k cap partial derivative with z is a vector differential operator, okay, and is read as del or Nabla, okay, and this operator can be operated upon a scalar function or a vector function, and depending upon whether it is applied on a scalar or vector, uh, it has different names, okay. So if it is applied on scalar function, we call it a gradient. If it is applied on a vector function as a dot product, then we call it divergence, and if it is applied on a vector function as a cross product, then we call it a curl, okay. So we are going to talk about gradient today. That means when this del operator is applied on a scalar point function, okay. uh, the gradient vector, or simply gradient of a scalar function f at point p naught, is the vector quantity given by this, okay. So gradient of f or del operator on f, okay, is written as del f or grad f, and is equal to this del operator, this right hand side applied on the function f, okay. So it can be written as I cap times the derivative of the function with x plus j cap times derivative of function with y plus k cap times derivative of function with z, and it's a vector quantity, okay, and its value is obtained by taking these partial derivatives, and these partial derivatives at the point x naught, y naught, z naught, okay, that means at p naught, okay. The geometric interpretation of gradient of a scalar point function. So let R be the position vector of a point through which the level surface passes. Okay, so we already know what is a level surface. We did it in differential calculus. Okay, so let there is a uh, level surface, and on this surface there is a point P whose position vector is R, which is xi plus yj plus ck, and if we differentiate this level surface with respect to t, so we get d phi by dt equal to 0, okay, so derivative with t, and on side constant, so derivative is 0, and since phi is a function of xyz and xyz they are functions of t, so by chain rule I can rewrite the left hand side as by using chain rule, okay. So phi is a function of xyz and xyz are function of t, so we know that chain rule, by chain rule we can rewrite it in this form, okay. So derivative of function with x, and x with t plus phi with y, y with t plus phi with z, z with t, okay. And the left hand side can be written as dot product of two functions, okay. So I cap phi x plus j cap phi y plus k cap phi z, and dot product with I cap phi xt plus j cap yt plus k cap zt, okay. So if we take dot product, we know that dot product of I with I is 1, so phi x with xt will get, okay. Dot product of I with j and I with k are 0, okay. So those two quantities will become 0, and similarly j with j will give value and k with k will give value, and other will be 0, okay. So we'll get exactly this. Now the first term in the bracket, you can see that is the gradient of the function phi, okay, and on the second bracket partial derivative with t will go outside, and rest is the position vector, so it is dr by dt, okay. So we can easily rewrite this as the gradient of phi dot product with dr by dt equal to 0, okay. And we know that dot product is 0 if the vectors are orthogonal, so that means gradient of phi is orthogonal to dr by dt. But r is the position vector of a function at any point on this level curve, so dr by dt must be tangent to the curve at p, and uh, since P is any arbitrary point on the surface, so that means gradient which is normal to this will be normal to the surface. Okay, so uh, gradient of phi is always normal to the surface phi equal to constant. Okay, so that's the geometric interpretation of the gradient. Okay, some of the properties of gradient. So if you have two scalar functions phi and psi, okay, and c is any constant, then uh, the gradient of sum is sum of gradients, and gradient of difference of function is difference of individual gradients. Okay, uh, the gradient of product of scalar functions is uh, obtained by using the same rule of derivatives. Okay, so derivative of uv is u derivative v plus v derivative u. That is still there in gradients, because gradient is also a derivative, okay, quantity or with respect to vectors. Similarly, gradient of phi by psi is psi gradient phi minus phi gradient psi by psi square, where psi has to be non-zero scalar. Okay, so this is also the same property that we have studied in derivatives. Okay, and gradient of c times phi. Okay, so the constant can go outside and it will be c times gradient phi. Okay, so these properties are easy to prove. Okay, and so the I take the next definition, which is about the directional derivative. So let a be any given point in the region of definition of a scalar point function phi. Okay, and let P be a point on any line drawn on one side of A. Okay, so if you have a point A and you take a point P on any one side, then the limit P tending to A, the scalar function at P minus scalar function at A divided by the length AP, if this limit exists, is called the directional derivative of function phi at the point A in the direction of P. Okay, so in the direction of AP. Okay, uh, and in particular, if we calculate this directional derivative along the coordinate axis, okay, and then we can generalize this to any direction. So let, if you have A as a point x y z, be any given point, and P is the point on the line which is parallel to x-axis. So P is x plus delta x y z, be a point on a line drawn through A and parallel to the positive direction of x-axis. So if you generate a space xyz and take any point A, then P is in the direction uh, which is parallel to the direction of x-axis. Okay, so clearly the length AP is delta x. Okay, which is positive when P is to the right of A. Okay, and so if we calculate the direction derivative at the point A in the direction of P, okay, then by definition it is limit P tends to A, function value at P minus function value at A over the length AP. And the function value at P means P is a point x delta x plus y comma z. So at phi value at this x delta plus delta x y z minus function value at A, so phi value at x y z divided by length, which is delta x. Okay, and when P goes A means delta x goes to 0, because AP length is delta x. Okay, uh, so limit delta x tends to 0 on this. Okay, which is by definition the derivative definition of the function with respect to x. Okay, the change in x divided by delta x. Okay, so it is same as partial derivative of function with respect to x, and we can write it as dot product I cap partial derivative phi with x dot product with I, because I dot I is 1, so it gives same as phi with x. And so we can write it as a gradient of phi dot I cap. Okay, because gradient is operator which is I cap partial derivative x plus j cap partial derivative y plus k cap partial derivative z, and we know that j dot I and k dot I are 0, so it will only give us back this thing only. Okay, uh, but importantly that the directional derivative along the x-axis is gradient phi dot I cap. So that means if we want to similarly calculate the directional derivative along say y-axis, so it will be gradient phi dot j cap. Okay, and the directional derivative along k-axis will be gradient of phi dot k cap. Okay, and so the directional derivative of scalar point function phi along x-axis is the partial derivative of phi with respect to x. Okay, so that's one, and so we can generalize this that the directional derivative of a scalar function phi along the direction of vector a is nothing but the gradient of function phi dot product with the unit vector in the direction of a. Okay, a cap is the unit vector in the direction of a. Okay, clearly it is I cap which is a unit vector in the direction of x-axis. Okay, similarly so the directional derivative in any general direction of vector a is gradient phi dot product with a cap, where a cap is a unit vector in the direction of a, and so we can calculate unit vector from any vector by dividing that vector with its magnitude. So a cap is nothing but a vector divided by the magnitude of a vector. Okay, so now we can say take few examples here. Say find the directional derivative of the function this at the point 2 minus 1 1 in the direction of the vector this. Okay, so we want to find the directional derivative of phi in the direction of this vector a, but at the point this. Okay, so first we know that the directional derivative of phi in the direction of a vector is gradient phi dot a cap. Okay, so first we have to find the gradient phi. Okay, but that gradient we know by definition gradient is always normal to this surface. Okay, so phi is a surface, so gradient is normal to surface, and so we have to find the normal, but normal we have to find at this point. Okay, and then we apply this definition to write that normal in the direction of this vector. Okay, gradient of phi. Okay, so phi is this, and by definition gradient of phi is I cap phi derivative x plus j cap phi derivative y plus k cap phi derivative z. So we know the simple derivative with respect to x, so we take partial derivative with respect to x, so y and z are treated as constant here. So if we differentiate this with x, it is y square, and derivative x is 0 here. So what we get is y square times I cap, partial derivative with y, so that will be 2xy plus z cube, so we get 2xy plus z cube j cap, and derivative with z, so that's 3yz square, so 3yz square k cap. Okay, and so we can calculate now this gradient at this point 2 minus 1 1, so x value 2 y minus 1 z 1 if we substitute here, so gradient phi will be equal to this. So this is the normal vector to the surface phi at this point 2 minus 1 1. Okay, and so we have to find directional derivative. For that we need a cap. A vector is given. Okay, so a cap is this vector divided by the magnitude. Okay, so we can calculate a cap as vector divided by its magnitude, so that means 1 square plus 4 under root. Okay, so 3, and so directional derivative will be just dot product of these two. Okay, so if we dot product these two, okay, and by dot product means I dot I plus j dot j plus k dot k, and I dot I is 1. Okay, so this is 1 minus 6 minus 6, so that gives minus 11 by 3. Okay, take another example. Say find the directional derivative of this surface at point this in the direction of normal to surface at this. Okay, so we have to write the directional derivative of this, so gradient phi at this point. Okay, and then in the direction of normal to this, so we have to find a vector which is has to be normal to this. Okay, and we know normal is always gradient. Okay, so gradient of this at this point will be a vector. Okay, so first we calculate the gradient of this surface. Okay, so it's the same function, so we know this, and at 2 minus 1 1 it will be this vector. Okay, so gradient phi is this vector at 2 minus 1 1. Okay, and then we have to find a vector, and a vector is normal to this at minus 1 2 1. So find the gradient of this. Okay, so a vector is gradient psi, where psi is this surface. Okay, so with respect to x we differentiate, so we'll get log z, so log z I cap. With y, so minus 2y j cap. With z it is 1 by z here, so x by z k cap. And at minus 2 1, if we calculate this, so we'll get minus 4j minus k. Okay, so we have gradient phi, we have a vector. For directional derivative, gradient phi dot product with a cap, so we have to find the unit vector in the direction of a. Okay, so this vector divided by its magnitude. Okay, so a cap is this vector divided by its magnitude, and so we take the dot product of these two to find the directional derivative. Okay, so gradient phi dot product with a cap, okay, which gives 15 by root 17. So take one more example here. Say find the angle between the normal to the surfaces. Okay, uh, where surface is this at point 412 and at point 33 minus 3. Okay, so there is a surface, and if we calculate the normal to this surface as one point, that will be a normal vector at this point. And if we calculate the normal to this at 3 3 minus 3, that will be another vector. Okay, so if there is a normal at 412 and another normal at 3 3 minus 3, what is the angle between those two vectors? Okay, so we know normal is calculated by gradient. Okay, so gradient of this at 412, gradient of this at 3 3 minus 3, and then we can apply the uh, angle rule. Okay, cosine of theta as and the dot product by magnitude. So given this surface phi is equal to xy minus z square, okay, the function, then the normal at 412, say we denote it by n1, which is gradient phi at 412. Okay, so gradient of phi is x derivative, which is y I cap, y derivative is x, so x j cap, and z derivative is minus 2z k cap. And at 412, so x4 y1 z2. Okay, so x4 y1 z2, so it gives 1 I plus 4j minus 4k. So that's normal to the surface at 412. Similarly, we can calculate normal to surface at 3 3 minus 3. So the normal, which is gradient phi, which is same as this, but now calculated at 3 3 minus 3. Okay, so it gives this vector. Okay, and so the cosine of angle is the dot product of these vectors divided by its magnitude, and we know the scalar product or dot product is I dot I is 1, so 3 plus 4 into 3, which is 12, and minus 24. Okay, so that gives minus 9, and divided by magnitude, which is 1 plus 16 plus 16, so root 33. 9 plus 9 plus 36 under root, so that gives root 54, and this way we get cos of theta, or is this, so theta can be calculated as cosine inverse of minus 1 by root 22. Okay, so this was the basics of vectors. Okay, so we did today up to gradient of a function. Okay, so in the next lecture we'll talk about uh, divergence and curl of vector. Okay, till then, have a very good day.